All right, we're going to see if we can put together the fundamental theorem of calculus here. To start with, we're going to start with a picture of a function. Now for our purposes here, don't know what the equation is going to be, but that's okay. I'm going to call this f of x. There's our curve. And we're going to give ourselves some boundaries going from A to B. Now we saw previously that if I wanted to know what is this enclosed region here, bounded by the x-axis, x equals b, x equals a, and the function f of x, we could find out that region by finding left Riemann sums, right Riemann sums, or even midpoint Riemann sums. The more rectangles that we put in together, we'll be able to come up with the exact answer. Well, let's say that we want to pick a value that's in between a and b. I'm just going to say that this is t. And I'm going to come up with an expression. I don't really don't need to know my region from a to b, but let's say I want to go from my region from a to t. So let's call this expression a of t, and that is going to be equal to the integral from a to t of f of x dx. Now what that allows me to do is it allows me to take that t value, that x value of t, and move it anywhere in between a and b, and it's going to come up with the area of that region like so, in between x equals a and x equals t. Well, I'm going to pick another x value, and what I want to do, I'm going to move h units away. And if I move h units away from t, that other x value that's right here is going to be t plus h. We don't know how big that is. We're just going to use the variable of h. So our goal is going to be, let's come up with an expression for that area in between t and t plus h. Well, if we're going to do that, we kind of need to go back to this expression that we've got here, this guy right here, and we need to use two of them because each one of them start at a lower boundary of a. I'm not going to be going from t to t plus h. I'm going to use this idea that I'm going to go from a to t. Well, to give me that region then, we could find a of t plus h and subtract off a of t. What that's giving us, my integral from a to t plus h of f of x dx. And let's say that that is the region in purple. And we'll subtract off the integral from a to t of f of x dx. And if we subtract off this region in blue, my picture's getting a little bit jumbled up here, but we are going to be left with what's in between. Okay, so we've got all of that. Let me erase the pictures and make it a little less cluttered, like so. So we've got that region, a of t plus h minus a of t. Now since I don't know the function, I don't know anything else about the region, I can come up with some approximations. Using the idea of those left and right Riemann sums, I can look at this, and if I took a left sum of that region in question, I see that I'm going to have too much area. So we could say that a of t plus h minus a of t has to be less than or equal to the area of that rectangle. Area of the rectangle is going to be the base times the height. Base is h times the height f of t. Now we're also bounded on the lower side. If we took do this in purple here, if we took a right Riemann sum, we would have too little area. So the area of that sliver, if I went with the right hand side, the base is h times the height of, now the x value that's in question here is t plus h, so f of t plus h. So the area that's in question that I really, really want is going to be bounded between the left Riemann sum and the left-handed rectangle and a right-handed rectangle. Now it comes time to play around a little bit with our inequality here. So I'm going to take this inequality, and because h is a positive value, I'm not going to change a single thing if I divide every single piece by h. Now what that leaves us with is f of t plus h less than or equal to a of t plus h minus a of t divided by h less than or equal to f of t. I'm also not going to change anything around if I play around with this a little bit. What if I change that value of h? Now, in that picture, h is a positive value, moving side to side here. But what happens if I make that h really, really small? What if I let h approach 0? Well, that won't change my inequality. Nothing changes here. I'll still be, everything will hold. Everything's going to be okay. So a of t plus h, t plus h minus a of t divided by h is less than or equal to the limit as h approaches 0 of f of t. So nothing changes there. My inequality still holds. Well, now if I solve those limits, as I let h approach 0 on the left-hand side, as h approaches 0, t plus h will just approach t. And so the value of this limit on the left-hand side, f of t. And on the right-hand side, there is no h, and so the limit as h approaches 0 of f of t is just f of t. Now what's left on the inside, this should look hopefully familiar. This goes all the way back to what we learned after we learned limits. This is a slope formula. I'm subtracting y values and I'm dividing by an x value. This is the definition of a derivative. The function that's in question is a of t, and so we're talking about the definition of the derivative of a of t. So that's a prime of t. Pretty sneaky how that got fit in there. So we know that f of t is less than or equal to a prime of t, which is less than or equal to f of t. Well, in order for that to be true, then a prime of t had better be equal to f of t. And if we know that a prime of t is equal to f of t, we know that they're antiderivatives. The antiderivative of a prime of t is a of t. And from what we saw in the previous section, the antiderivative of f of t is capital F of t. Now, because we took that antiderivative, we do have our plus c. Because we could, if I derive it to check, sure enough, the derivative of a of t is a prime of t. The derivative of capital F of t is f of t. And the derivative of a constant is 0, so we're okay. So now taking this, we already saw what a of t was. A of t was my integral from a to t of f of x dx. Let's come up with a specific value. Let's see what happens here. I want to find out what is a of 0. Excuse me, a of a, not 0. A of a, which means that I'm finding the integral from a to a of f of t dt. Excuse me, f of x dx. Let me erase that there. F of x dx. Graphically, that's taking that function and saying, okay, what is, if I add together all the rectangles from A to A, if I add all those areas together, what am I going to get? Well, obviously when I go from A to A, the base is 0. There are no rectangles. The area underneath a single point is 0. So we can say that A of A is equal to 0, which means that capital F of A plus C is also equal to 0. We can say this part by that substitution because of A of t is that formula. Well, that's awfully handy because with doing just a little rearranging, I know that capital C is equal to the opposite of F of A. Let's try another one. What if I had A of B? Well, that means I'm going with my antiderivative or my integral from A to B of f of x dx. Well, if I use the other expression that we just had, A of B is capital F of B plus C. Oh, now wait a second. We just came up with an expression for what C was. C is the negative or the opposite of f of a. So what we've run into by plugging in, doing a little substitution, my integral from a to b of f of x dx is equal to the antiderivative of f evaluated at b minus the antiderivative of f at a. And that is the fundamental theorem of calculus. Let's try this on a function. Let's say we would take the function y equals, let's go 2x. Y equals 2x. And let's go, drawing that function in, let's go from 0 to 2. And so I know that that's going to be the coordinate 2, 4. And let's find out what is the area of this region. Now we know what the answer should be. We know that because that's a triangle, this area is going to be 1/2 times the base times the height. So we should get an answer of 4. Using the fundamental theorem of calculus, though, this is saying, okay, let's take the integral from 0 to 2 of 2x dx. The antiderivative of 2x is going to be x squared. And we're going to evaluate that from 0 to 2. This is the notation that we'll use after we take the antiderivative. My boundaries are from 0 to 2. And so our f of b, our capital F of b is going to be 2 squared minus our capital F of a, 0 squared, sure enough is 4. Now we'll work through a number of other examples to show how this works and what happens if if the area that's in question is below the x-axis and how that plays in. But this is just a little idea of how the fundamental theorem of calculus works.